Okay, glad you were all here in class on time. Today we're going to transition into talking about network programming. In particular, this will be the core material that you need for the proxy lab, which is the final lab in the course. To review, for some of you, or maybe this is the first time you've thought about this, client-server model is the typical model for network applications. You have some sort of server process that's running, and one or more, it's serving one or more client processes. Okay? So there's just one here. And the server is managing some sort of resource, and it provides a service using that resource. So if the client sends a request, then the server handles that request and returns it, the response back to the client. The server is activated by the fact that the client makes the request. Otherwise, it just sits there passively. And it says, think of a vending machine, right? Until you actually put your money in and press the button, the vending machine just sits there doing nothing. Okay. Important to note that these are processes. Typically, we think of them as the client running on one host machine and the server running on another host machine. But you could have multiple client processes running on the same host. You could have a client running the same host as the server, and so forth. Okay. So we've seen many versions of this picture in this course. Just a reminder that the network piece is here, and it's just off the same I/O bus that, for instance, the disk controller is. Right? Okay, so the path is through the I/O bridge to the I/O bus to the network adapter. Okay, so in terms of networks, we think of them as this hierarchy of boxes and wires, and at the first level, it's called, at least in Microsoft terminology, although I'm not sure how widespread the name is beyond that, what's known as a system area network, which will span a cluster or a machine room. I put a little asterisk here because another type of setting in which the SAN abbreviation used is in the storage area network. Okay, that's something that a disk provider, solutions provider, storage solutions provider would have to enable a whole bunch of your computers to talk to sort of dedicated fancy storage devices. It has the same SAN abbreviation, which is why I highlighted it. But for the purposes of this class, we're going to talk about the system area network. Then you have what's known as a local area network, which can span, say, an entire campus or a building. And it says here, Ethernet is an example. Then you have the wide area network, which can span all across the country and all around the world. Okay. And then there's the notion of an internet network, or internet for short, which is just a interconnected set of these networks. Okay, and in this course, we want to make the distinction between sort of the lowercase I internet, which is just the generic term for any network that connects up other, say, multiple LANs and so forth, and the internet that we're all so familiar with, which is with a capital I in this course, sort of the global IP internet. Okay, so let's see how you build an internet from the ground up. You start with a Ethernet segment that's based on this hub, okay? And you have the hosts, these are just the machines. These are just the different machines. And they're connected to the hub by twisted pairs of wires, right? And the connection here is called a port, okay? And it spans a room or floor in a building. The Ethernet adapter each Ethernet adapter has a unique 48-bit address. You may have heard of it, it's called a MAC address. Okay, and then a host can send bits this way, packaging them up in something that's called a frame. And then what the hub does is it just basically broadcasts. So it gets whatever bits it sees, whatever frames it sees, and it sends them along to all the hosts. So every host sees every bit. Okay. Now, just an aside, this is sort of the classic way to sort of build up from the bottom these networks. But for most installations today, people don't even bother with hubs. They used to be have sort of economic advantage to having these hubs, but now bridges that we're going to talk about next, switches and routers have become cheap enough that people tend not to even bother with hubs. So what are one of these bridges? A bridge, which is like shown here, connects a series of hubs, and you can have, for instance, this bridge connects these hubs that are all on 100 megabit per second links, and similarly down here. But between these two bridges, we actually have a faster connection, right, a gigabit per second. And what's interesting here, we said that the hubs are kind of naive about things. They'll just take whatever gets sent to them and broadcast it on all the other hosts on the hub. The bridges are a little bit smarter. They figure out that which hosts are reachable across which of their ports, and then they're only broadcasting information where that's where the host is. So, for instance, if you're going to send from up here to down here, from A to C, for instance, then it would go ahead. This bridge would go ahead and send that information along here, and then it would go this way, so be more routed. But for instance, it would not send it along this path here, or this path here. Okay. So it's a little bit smarter than just broadcasting. Okay. So for simplicity, often see pictures that look like this, where the hubs, bridges, and wires are all just sort of collapsed into just a single thing that looks like a long bus, and then a bunch of hosts connected off of that. So if that's our picture of a local area network, then if we take a couple of these guys and hook them up, that's how we get the next level up, okay, via routers. You can have routers here, all right? And these routers are, as the name implies, they're responsible for routing the traffic from this local area network to this other local area network. And the interesting thing is that these LANs themselves can be completely different types, right? So one may be an Ethernet, like we said before, but one may be a T1 link, right? A really bulky, powerful link, and so forth. And so it's as we'll see, it's the job of the protocol that the router is going to use to be able to do these kind of translations between the sort of what what this LAN speaks versus what this LAN speaks, right? Okay. And then this is starting to look more and more like a picture maybe you're familiar with. You have hosts, all around the world, and then you have these routers in the middle. Obviously the hosts are interspersed as well. And then you have routes between these routers, right? So paths you can take between these routers. And so in general, lowercase internet, that's what we describe as just connecting up a collection of these local routers. And for instance, you might find something like that within a large company, right? They may have their own internet that's not the public internet at all, but it's a way of connecting up the machines inside their inside, say, a large corporate building. Okay, and so if this host wants to send to this other host, then there's just a hop-by-hop routing process that takes place. And what this picture is showing is that there are multiple routes between any pairs, which is good in case there's like congestion along one route or failure along one route. And so what can happen is that even between this host to this host, you can have some of the packets go along one route and some of the packets go along the other route. And as a result, it's up to the overall protocol that we'll talk about in a minute to sort that all out, okay? To make sure that you see the packets in the order they were sent. Okay. So this is what I was just mentioning, that if you have these incompatible LANs, okay, that don't have the same features and speak the same protocols and so forth, internally, then you need an overarching protocol that will allow each of these LANs to speak to this protocol. Okay, and it's just a set of rules that governs how hosts and routers should cooperate when they're transferring data. And therefore, it sort of abstracts away or hides away or smooths away the differences between different networks. Okay, so in the next level of detail, what do we need? We need a way to what's called name something we want to send a message to. Okay, so that's a naming scheme. We need a way for one host to be able to identify another host such that they can communicate. Okay, and that's a naming scheme. And then the other thing it needs is some delivery mechanism, right? Some way to actually get packets from one host to the other, from the source to the destination. So a naming scheme is based on what's called host addresses. So every machine will have a host address. And so the thing about the host address is that it uniquely identifies the host. Okay. You can have, of course, multiple host addresses for the same host, but you can't have a single host address refer to more than one host. Okay, so that's what I mean by uniquely identifies. You can have multiple ones mapped to the same machine, but you can't have the other way around. Okay, so delivery mechanism, we talk about this notion of a packet. Okay, and a packet, as you may have heard, there's always a header part and a payload part. And the payload part is just the data, and the header part is the routing information. So it includes things like the packet size and the source and the destination. Okay, what's the host address of where this packet is coming from, and what's the host address of where it's headed. All right, so here's a little picture. We have our two LANs, and we have a router. Okay, very simple in this case. And so the client wants to send some data, and the protocol software that's running with respect to this LAN says, okay, I'm going to put a packet header on it, internet packet header, but then for purposes within this LAN, I'm going to have what's called a frame header. Okay, so that's specific to the LAN, or you know, there's a few families of them, but it can be specific to that family of LANs. Okay, and so this header is used to route sort of this first half of the journey. Okay, and that gets sent to the router, and then the router has to know how to do these translations. So it has to know how to convert from this frame header to the one that this second LAN uses. Okay, so it could be very different. All right, and then also it needs to know how to interpret the packet header and route the thing to the right place. And eventually it gets to this LAN adapter, who will return to the protocol software that will strip off the packet header and the frame header and return the data, or deliver the data to the host. Okay, any questions on that? Yes?
What's the point of the frame header? Why is that necessary if it's just being replaced?
Because the frame header is what's used to within the LAN. So I mentioned in an earlier slide that each LAN communicates between the hosts, like through the hubs and bridges, in units of what's called frames. And those frames have headers and payloads. And so all the routing internally to a particular LAN, you know, whatever path it has to take, is in units of frames and needs to have a frame header. So it's a sort of it's equivalent of the packet header, but within this LAN, right? And then once you get out into the greater internet, then you need the packet headers. Okay, yes?
What data is contained within the frame header and within the packet header?
The packet header is going to contain the information needed to do the sort of the global routing, right? So in this case, it was just the right, you know, various info such as the packet size and the source and the destination addresses. Okay, the source address is needed for identification, basically. So the other side knows who sent this message. Destination is used for the routing on the way. Okay, the frame header is similar, but the sort of the information is relevant to routing within this particular lane. Okay, so whatever the protocol is for putting in headers and so forth. So for instance, you can imagine that these headers here could use local names, right, for these hosts, right? Could have a naming convention, have their own naming convention for if I have a local area network and I have whatever 3 servers, 3 hosts, machines, and I give them names that are local to me. I just give them names, and then that is what these frame headers use to route locally. They don't have to be globally unique names, okay? But these guys need to use the globally unique names. Yes.
So in this process, is there ever a time when the packet is like missing its frame header between the LAN adapters, or does it get frame header 2 as soon as it loses frame header 1?
Right. So if we'd shown more hops, there'd be no need for. You could strip this frame header off as soon as you started the routing part. And if there's a bunch of hops, boom, 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 and it's only when you arrived at this at the LAN here would you now, for instance, maybe know, you do a lookup and say, oh, what is the protocol, frame header protocol I need for this particular LAN? Now I'm here ready to deliver the packet, and that's when you add this on. So, the picture was simplified because there was basically just the one hop. Yes?
So does the data ever get to the server host B? Or does it just stop at LAN to adapter and somehow get blocked? Because the arrows go in different directions, I can't really follow that.
Oh. Yeah. Good catch. Yeah, okay. Good. Yeah, you wouldn't be happy with that network. It's a write-only network. Okay. Good. So there's a number of issues that are glossed over by this simple example, in addition to the ones we just talked about. How do the routers know where to forward the frames? How are the routers informed when the topology network changes? One route goes down and gives you replaced with another route, for instance, or just a route gets added, new route gets added. What if the different networks have different maximum frame sizes, right? So one says that my frames are tiny, one says my frames are big, and the one who's sending tries to send a big one to the one who's tiny, right? And you've got to break them up and so forth. And what if a packet gets lost along the way? Okay, so all these kinds of questions are entire area of computer science called computer networking, and there's a whole course you can take on that to discuss this and many other issues of computer networking. But in this course, we're just going to focus on the things that matter to the programmer. Okay, so all right. So so let's talk about now the uppercase internet. Okay, and the uppercase internet, the internet we're all familiar with, is based on these TCP/IP protocol families. So the bottom level of that is the IP Internet Protocol. Okay, anybody know what that does? So it provides this basic naming scheme that gets you from a host to a host, so from machine to machine, and the capability of delivering packets, which it calls datagrams, from the host to host. So we haven't gotten from a process to process, we've just gotten from a machine to machine. And then there's 2 types of protocols on top of IP. One is UDP and the other is TCP. And TCP is the one that most of us are familiar with. But UDP is used sometimes to avoid some of the overheads of TCP. So if you want something that's has higher performance and you're okay in your application for whatever reason with some amount of packet loss, then you might go to the UDP route. Okay, so this, as opposed to host, does go process to process, which is what you want, right? So for instance, the client process we talked about, server process on that first slide, but it is unreliable. Okay, it's best effort in other words. Okay, it doesn't purposely try to be mischievous or anything like that, but it's just sort of best effort. Okay, it's going to send your packet along its way. It's going to avoid all the overheads of the TCP. But if there's some congestion, the packet gets dropped, then you know that's a possibility, and your application should expect it. Okay, so far more used is what's known as TCP because it basically it still does the process to process as in UDP, but it's reliable in the sense that you know, if you send packets from a source to destination, then eventually it'll get there. Okay, and the TCP protocol will you do retransmissions and so forth in order to make sure that happens. And it also has this notion of a connection. Okay, it's kind of like a phone call, right? You've connected someone making a call to somebody receiving the call, and you're going to send the packets along this connection. Okay. Now, in Unix, as we've seen in the past, basically everything is mapped to a file, and including things over the network over the network. Okay. So when we get into it in a few slides, you'll see it's a sort of a familiar interface, as if you're just reading and writing files, but instead you're going to be reading, writing to things that look like files, but they're really connections. Okay. And it's going to use something that's called the sockets interface that we'll talk about. Okay. So here's how it looks. You have a client, has some user code. There's via socket interface will make you know, express desires of things to be read and written to the network via sockets interface, and system calls that go into the kernel. The kernel is running the TCP/IP protocol with the server on the other end. You've got the network adapter we showed before, and the routing over the internet, and so forth on this side. Okay. So the actual TCP/IP protocol that's trying to ensure this reliable delivery of these packets is basically hidden from the user, from the user code. Okay, so from the programmer's point of view, hosts are mapped using 32-bit IP addresses. Okay, now you probably haven't seen them expressed very often as in sort of 32-bit notation. You've probably seen them expressed much more often in this form, which is sort of the conventional way of writing out an IP address, which is basically just that 2 bytes at a time you write out in decimal notation what the things are. Okay, so that's why you see things that look like 128.2.203.179. So these IP addresses, some subset of them, are mapped to internet domain names. Okay, this is something you're also familiar with from doing web browsing or anything, right? So like www.cs.cmu.edu is the domain name that this IP address is mapped to. Okay, and process on one host communicates to process another host over this connection. Okay, so when I talk about 32-bit IP addresses, it's the long-standing protocol IPv4. Okay, and way back in 1996, so what is that, 21 years ago, people said that's not going to be enough addresses, enough bits for addresses. Let's come up with 128-bit addresses. And so they came up with IP version 6, which had other nice features as well. But the interesting thing was that the adoption has been almost non-existent, right? It's from 1996 to 2014, right? Only 4% of access to Google services were actually using the new IPv6. Okay. Now, in the very recent history, it looks like it's trending up, and so maybe it's finally taking hold that people will switch to 128-bit IPv6 addresses. But for now, we won't worry about that so much. We'll keep in the book and the lectures to focus on IPv4, where internet IP addresses are 32 bits. But importantly, we're going to talk about how you can write your code that's protocol independent, that no matter whether your proxy in your proxy lab is talking to something that's IPv4 or IPv6, it's going to work, okay? And basically because we'll have wrapper functions that will hide the difference from you, so you don't have to worry about whether it's IPv4 or IPv6. All right, so that was the side. So these 32-bit IP addresses are stored in this structure called the IP address structure. It just contains, 32-bit unsigned address. So one important thing, we mentioned this when we talked way back about byte orders. Most everything that you've been working with so far has been little endian, okay? But we mentioned back then, and we're reminding you again, that network packets are the other way around, they're big endian, okay? So the first byte is the most significant bits of the 32-bit number. All right, good. This is just talking about the dotted decimal notation I mentioned, that you take these pieces like F2, and you say, and the decimal number for F2 is 242. And then there's functions that were provided, get address info and get name info, that we'll talk about at the very end of this lecture, unless we run out of time. And then that allow you to convert between IP addresses in dotted decimal format. Okay, you give it one and get back the other. So you're probably familiar with thinking about how these domain addresses work as this kind of hierarchy. So we start with the root, and then we have the .edu and the .coms and so forth. Under .edu, you'd have things like CMU, cmu.edu, right? Under CMU, you'd have maybe CS and ECE, and under CS, you have our ICS, and then things like Whale Shark and all the other sharks. And PDL is a CS and www. And eventually you get to a leaf in this, and then you get the full IP address in the dotted format. And this is also showing like Amazon.com, www.amazon.com. This is the IP address for Amazon.com. Okay, so you can talk about first level domains, second level domains, third level domains based on this kind of hierarchy. So any questions on that? So DNS, you may have heard of it, stands for Domain Naming System. Mainly you hear about it when it's not working, okay? So if you're having trouble, connecting to anything, sometimes it's because the DNS server is congested or not working or whatever, and so you're not able to get the translations. So the DNS maintains mapping between these IP addresses and domain names. Okay, so it's just this collection of host entries, again, which are just a set of domain names and IP addresses, and it just allows you to map between them. So there's this function called NSLOOKUP, which allows you to specify a www. A name and get back its IP address in the dotted format. Okay, and so we're going to look at some examples in this slide and the next slide. The first example I want to point out is that there's always, every host has a way of talking about itself. Okay, you could talk about, as a host, you could talk about yourself by actually knowing what your domain name really is. But then if you take that code, it's not portable, right? Every time I move that code to a different machine, then I'd have to look up, what's my IP address, and plug it in there. So to avoid all that complication, there's this magic one, 127.0.0.1, which wherever you are on whatever machine you're on, if you express that address, it means me. Okay, I'm talking about me the machine I'm currently on. So that can be very useful, okay, to have that whenever you want to actually refer to yourself when you program on a machine. Okay, 127.0.0.1. Okay, so then there's also something called host name, which can determine the real domain name of the local host. Okay, so sort of the flip of that, right? So this code, this particular snippet of code was obviously run on the Whaleshark machine, which is why it's returning Whaleshark. Okay, and you can go backwards. So from Whaleshark, right? I can do an S of lookup and I get its IP address. Okay, and that was what we showed in the previous slide. And then you can have things like, that's a simple case when there's just this one-to-one mapping. It turns out that you can have multiple domain names, like here we're showing CS and ECS MIT, that map to the same IP address. Okay, and I double-checked that this morning, and that's still the case. That if you do an S of lookup on each of those, you'll still get the exact same address. Okay, so it's possible to have that kind of thing. You can also have the flip side, which you may be familiar with. If you have a really popular site like a Twitter or Google or whatever, it's going to have a whole slew of names of domain of IP addresses that all correspond. Okay, and so any service has choices, right? And that's just a way of sort of increasing throughput, balancing load, and so forth. And this is just showing that when I ran the same command twice, in this particular case, I got the exact same 4, but the order got different order, so no big deal, right? And so forth. Now, there are some cases where we can have a valid domain name, like our ICS domain name, but we don't have any IP address mapped to that. And so if you run an NS lookup on that, it'll just return nothing, right? You won't see it, instead of seeing a list of addresses, address colon, blah, 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 it'll just be blank. Yes?
If you have, like in the last slide where two things map to the same IP, how do you differentiate, like if you want to tell one network one thing, like how do you tell something to cs.mit.edu versus EECS?
Yeah, so the notion here is that they're trying to give people multiple ways of getting to the same machine. Okay, so they're not it's a good point. By mapping them to the same IP address, you're basically saying there's just this one host machine that's serving both of these.
Oh, okay.
Okay, yes.
How are these like IP addresses registered? Like, why can't I just have like Amazon's IP address? Is there like some centralized thing, or how are these like unique?
Yeah. There's some like if you've seen commercials for things like GoDaddy and stuff like that, there's these companies that will that sort of run the naming system, and they'll for some fee they will register. You give it a domain name, it looks up to see if it's already claimed. If it's not claimed, then
What is it looking up on? Like is there like a central database for like all?
Yeah, yeah, there is. There's a repository. I mean, DNS will have all the mappings as well, right? Yeah, I'm drawing a blank on the name for that repository, but does anyone remember? But there is. Yeah, so you have to negotiate. I mean, originally this was all sort of done more centralized. I mean, just like there was a single entity that was in charge of doing all this domain name processing, and then they decided that the government didn't want to be bothered with that anymore, and so they sold off the rights to private companies. And private companies, if you go to like a GoDaddy or something like that, you'll see that the fee they charge is really small, but they're using it as a way to send you a zillion advertisements and things like that, and try to get you to use their services for like creating web pages and you know, administrating your websites and stuff like that. So there's ways they make money beyond just that's the real ways they make money, and they just sort of as a hook provide a service that will allow you to register a domain name efficiently. Yes.
I think it's ICANN, the Internet Corporation for Assigned Names and Numbers.
Okay, yes,
This is
good.
the one, and they have a number of registrars. VeriSign is the one which does the .com domain.
Okay. That makes sense. Good. Thank you. All right. Okay. So we talked about these connections, right? Like this, you know, point to point, like a telephone call between the client and the server. Like a telephone call, it's full duplex. You can go, you know, either direction. Reliable. That's if you're doing the sort of the TCP part of the protocol. Then what that says is the stream of bytes sent by the source is eventually received, right? There may be a number of retries and so forth. Things could even crash, you come up, and then you send it much later. But also the notion that the order is maintained, okay? So anybody know or can think of a simple way to make sure the order is maintained? I've got these packets, they're going along different routes, so not arriving in the same order they were sent.
Label the packets.
What?
You can label the packets. This,
With,
like a number.
yeah, sequence numbers.
Packet 1.
Yeah.
Packet 2.
So you just said, this is another thing that would go in the header, right? You get the sequence number. So you say this is the, you know, the 10th packet along the stream is the 11th. And then at the receive end, you're getting these packets and you put them in order, right? And that's also how you know when one was missing. You see 9, you see 11. You wait a while, 10 didn't show up. You say, oh, okay, I better tell the source to resend me 10 because it never showed up. All right, good. Okay, so a socket is an endpoint of connection. So for any one connection, you have the endpoint on each end of it. And a socket address is simply just the IP address and what's called a port, okay? So a port is a 16-bit integer, so slightly smaller, that identifies a process. And there's two types of ports. The well-known ports are conventions that are set up to say if this port means something, okay? So port 25, if I'm talking to a particular host machine on port 25, that's because I'm sending email. It's about email. Okay, that's a convention. If it's port 25, it's email. Port 80, as it says on the slide, that's web service. Okay, and I'll show you some further examples on the next slide. But the other type of port is what's called ephemeral port. There we go, ephemeral port. And that's ones that come and go, okay? So like if you're a server and there's a bunch of clients coming in, you need a port for each of those clients. Each of the connections, then you can automatically assign numbers and so that each client gets his own. Okay, so here's a list of some of the well-known server names and ports. So like we said, the web servers, the port is 80. And the service is the HTTP. Okay, email servers speak SMTP. You may have seen that if you try to set up your email client over port 25, as I mentioned. SSH, you probably use that a lot. That's port 22. FTP is 21. And Echo, which is, I don't know how often you use that, but it's good for examples in class, so that's why we highlight it. It's port 7. And if you ever want to know on your machine, on your Linux machine, what ports are already well known and established. More this etc services file, and you'll see a list. There's usually 40 of them or something, not just 5. Okay, any questions on that? All right, so this slide has a lot of numbers on it, but it's actually fairly conceptually easy. So you've got this client host address that's here, okay? And then we said the connections are always host address and ports. So it's just repeated here. The red is just repeated, okay? And similarly, you have a server, and it has this IP, and then I've repeated it here and here, okay? And then this is a web server, so it's port 80. So you talk to it by colon port name, was 80. Okay, and this client was one of these ephemeral ports. Okay, and it just so happens, I mean, it could be arbitrary, just happens that this is 51213. Okay, and so that's also why it's here. All right, so this IP address port identifies, the endpoint, and same over here. And then if you're looking at the pair of them, that's a connection. We have a connection between this guy and this guy. Okay, so a lot of numbers on this slide, but it's really actually only conceptually pretty straightforward what's going on. Okay, so so you have this client, and this is its and it's trying to reach this server. Okay, so it says, okay, this is the server, and it so happens that I want to talk to this server runs, this host runs many types of servers. One of them happens to be the web server. That's the one I'm interested in, so that's why I have this 80 here. So then that's why this gets routed to the 80. Okay. Conversely, if instead you put a 7 here, then when it got to the operating system kernel on the server host, it'd say, oh, I see the 7. I'm going to route it to the process that's running the echo server. Okay. So that's why you have to append the ports, because that's the only way the kernel knows sort of which server process to send it to. Okay, so so as I mentioned, we're going to use a socket interface. It's going to look like we're just like writing to files, but they're going to be writing connections, and that will mean transfer this, read this in from the network or write this out from the network. This convention has been in place since the early 80s. It's part of the original Berkeley distribution. That's interesting that already contained an early version of the Internet protocols, even though the Internet was just sort of barely ramping up. And but not just Unix, all the other major operating systems also use a socket interface so they all have the same conventions. Okay, any questions on that? Okay. So what is a socket? This endpoint of communication. Socket is a file descriptor, as I mentioned. So there's going to be a client file descriptor and a server file descriptor, and again, by either reading or writing to that quote-unquote file, you're actually sending along the network. So I think I talked about this. So the main distinction between what you've seen before in terms of regular file and O, reading and writing to files, is and these sockets is that there's slightly different convention for how these things get opened. So for a file, you just say open, blah, and close. But here, because we're going across different hosts and so forth, there's more steps involved, and we will see that later in this lecture. Okay, now we're ready for the quiz. You know what, though? I bet, because I got late, started so late, I bet it's closed. Let me open it. Yeah, sorry, we got started in the class 20 minutes late, so the quiz isn't open. Open it first. We'll get there. Can you see it now? Yes? Okay, good. All right, so how do people do? Excellent, all right, 83% knew that the local host was 127.0.0.1. 87% knew that 80 was the web service port number. And 85% got the networks in the proper order, smallest to largest. All right. Easy stuff, good. Either the questions are easier or you guys really understand this material. Maybe a little both. Okay. All right, so we're going to run through in the remaining 13 minutes as far as we get sort of the concrete example of a very simple server called the Echo server. And all the server does is it just takes a client will send it a message and it will just echo it back. Okay. And so repeatedly the client will read a line from the terminal, send it to the server will send it back to the client, and then the client will print it out. Okay? So it kind of looks funny, but what's going on here is that, and this program is called Echo Client. So Echo Client gets called as so, okay? And that, if you look here on the server side of things, you get print back a message that says, okay, I've been connected to a machine, this Bamboo Shark machine, and here's a port number. All right, and then what happened was the client typed this line is being echoed, on the keyboard, and that caused 26 bytes to be sent to the server, okay, because that's how long that is, okay, and then the server turns around and sends it back to the client. And the client, when it gets those exact same 26 bytes back, prints it out. So this line is being echoed. Okay, then it goes on to C, types this one as 2, and that's the 17 bytes the server receives. And then it gets back to the client, it prints it out. Then the client exits, okay, out of the program, and that's fine. And now we re-execute the program. And the second time we get connected and we happen to get a different number, right? Different port number, right? These are the ephemeral ones. And so then in this new one, we type this one is a new connection. And again, the server gets those 29 bytes and echoes it back, and then it gets printed on the screen. This one is a new connection. All right, so that's kind of how it's going to proceed. Pictorially, what's going on is you have what happens to the client, what happens to the server. The first command was when we started up the server code, that started up the server. Okay, and so the server got all ready to accept client requests. So it's just sitting there waiting passively. Right? It's like your vending machine, just waiting for someone to put coins in there. Then the client was started up. Okay, and there's some client file descriptor that it's going to do the writing to, and it makes a connection request. That request gets accepted by the server, and now there is this connection established between the two. Given this connection, you're in this loop where you read what's been typed to the terminal, and then you write that to the socket that gets sent across the network. And then there's a socket read on the server side, and then since it's just echoing, all it does is just turns around and writes that right back on the socket going the other way. That gets read by the socket, and then you write to the terminal, and then you repeat. Okay, so that's the equivalent of the example session we saw before. Then eventually this gets closed. Okay, that sends the end of file. Then when you try to do a socket read here, you get there's end of file, and that triggers a close, and so that connection is closed down, and you go back to a state of waiting for connections. Okay, and this is showing a case where there's just a single client. So, but in general, the server can have accepted a whole bunch of connections, and then when you do a close, you drop that one particular one, but you're still servicing the others, and so forth. Okay, any questions on that? Okay, so now what I'm going to do is, disconnect client, drop the client. So here, the only thing that's changed from here to here is that we've actually spelled out what the socket read and socket write are at the next level of tail, which is that the terminal read is by fgets, right? And later the terminal read will be by fputs, okay? And then you remember and I have slide review, we have this, the Rio package that we have with the course that allows you to write and then read from a buffer and write and read from a buffer, okay? But otherwise, this exact same thing happens, okay? So here's the reminder. In Rio, we had a read end and a write end. In this case, we're just using the write end. Never returns, so it just writes out up to n bytes. Okay, so when you know exactly how many bytes you're going to write, which you typically do, if it's like you're sending you've collected and then you're ready to send something from a buffer, you know the size of the buffer, and so that's why you can use the write end. When we're doing reading, we're doing this reading from a buffer. Okay, so it reads a text line of up to max length bytes from the file denoted by this file descriptor and stores it in this line user buff, and especially useful reading text lines from network sockets, which is what this whole thing's about. It has the stopping conditions that when you hit the max len bytes read, you encounter an end of file or you encounter a new line. Okay, that's why it says text lines, right? So every time you encounter a new line, you consider that one done with. Okay, so that's sort of the review. And then based on that review, then we can start to figure out this code. All right, so this is the on the client side. So what's going on here is that you're going to pass it the host and the port, okay? And it's going to open a file descriptor. And remember we said that you needed both the host and the port to sort of uniquely identify things. So it will open a file descriptor based on that and give you a client FD. That'll be one of those ephemeral ones. And then what you're saying, okay, so then I need to initialize. I use the read initialize buffer version, where I give it that descriptor and then this pointer, just the Rio type. Okay, so then we go with this loop. I do an fgets, which is just going to read from the terminal, from standard in, up to a max line, put in this buffer, and then I do this write. Okay, I know I pass the length of the buffer, the length of the string in the buffer, and I do it to this file descriptor, right? So that's going to say write along this channel to the server, right? Then I wait for the response. I get this response back, and I just read it into a buffer, and then I echo it out to the screen, out to standard out. When I terminate out of this because of a null, then I go ahead and close that file descriptor and exit. Okay, so it's just showing the code that executes what the diagrams we showed were on the previous slide. Okay? So again, it's just the code of F gets, write line, read line B, and F puts, right? F gets, write line, read line B, and F puts. Okay, so that does this part here. On the server side, okay, what do we need to do? We need to get ready to listen, so we need to just open a listen file descriptor, okay? And so that creates this little, we get the file descriptor here, and that means we're ready to accept connections. Then I'm going to, in the interest of time, I'm going to skip this a little bit. You can look more closely at this and also in the book. But the basic idea is that we want to be able to accept incoming connections. Okay, so a connection comes in, it's from some client address, and we go ahead and establish a file descriptor for that point. And then we're going to use this get name info function that we'll talk about probably next class, that allows you to do the translation, basically just so you can print out this message. Right? Remember we said connected to host name and port. That was part of the interface. It's not strictly necessary, right? It was just to make our sessions, right, this first